My guest today is Kevin Kirchman.
Today, we're going to discuss why the greenhouse gas theory is invalid scientifically. And as we discussed, Tom, it's important to challenge the science. If the data is conflicting, or we see any alterations to the data, and the theory is not panning out as the models are predicting, then maybe we should look more seriously at the theoretical foundations of what we're calling the science. So basically, that's what I've done. This chart is a relatively common one. It's the Earth's spectral radiant spectrum, and it shows these little, I call this the CO2 bite. Okay, so this is where CO2 is reducing the energy that's emitted to space. In other words, is absorbing the energy. Okay? So the greenhouse gas theory goes, because CO2 and other gases are absorbing energy, the Earth is warming. Okay? But there's fundamentally a problem with this idea, as this chart shows. So technically, the Stefan-Boltzmann law is a thermodynamic mathematical relationship that shows how the temperature is in proportion to the energy under the spectrum, and it was the area under the spectrum divided by the Boltzmann constant and the emissivity for a gray body, and that's it for any body in space, basically. This E, then, what we're saying is CO2 is reducing the area under the curve. Okay, so fundamentally, that means T is going to be smaller by the Stefan-Boltzmann law. So if T is small, that means the temperature is cooler, right? So we say the greenhouse gas theory, because it's blocking the radiation, the Earth must be getting warmer, because we're relating that to conservation of energy. We're saying, okay, so the energy is getting is being absorbed, therefore the Earth must be getting warmer. But the radiative spectrum is saying something else. It's saying, wait a minute, you can look at the absorbed energy as somehow warming the Earth, but we don't. That's not what the picture says. The picture says the Earth looks cooler when you look at it from space. Okay, so this is an observer in space would say Earth is cooler because of CO2 blocking the energy, and that's because the area under this spectral curve is less than otherwise. Now what I'm going to do is provide some supporting evidence and other explanations for other parts of the theory that people want to use to continue to defend it. All right, so this is a really important idea here, Newton's law of cooling. Newton's law of cooling says warmer objects radiate more heat. Okay, so this is and this is Wien's law over here. It says basically the same thing. It says as the temperature of a body increases, then its radiative spectrum is increased. Okay, you can say the different temperatures and the different, and obviously the higher the temperature, the more energy is under the radiative spectrum. This is the same. This is for the sun, for example. Okay, so the question is, okay, if the greenhouse gas theory were valid, then the Earth will be radiating more energy, not less. Okay, so if it's not, and what we've just seen is that it's radiating less energy. So the question is, where is the extra energy? All right, so this is a quote from Einstein. He's, basically, we've got to question and challenge these problems from new angles, and this is the basis of innovation in scientific study. Okay, so this is these are actual Earth spectral radiance from a thermal emission spectrometer on the Mars Global Surveyor back in 1996. So basically, this was a vessel, a spacecraft, going away from the Earth on its way to Mars, looking back at the Earth and looking at our spectrum. And this is a really interesting curve here, and I'm going to show two of them. Again, it shows the CO2 bite. You'll see two graphs here. One is the wave number, and the other is the wavelength. Then they're kind of inversely proportional, so they're kind of flipped backwards. But the wavelength is the one I like to work off of, because it basically shows because the shorter wavelengths have higher energy, and so this though is the energy curve, so you can understand the relationship better. This is where we start at. This is the CO2 bite, and again, this is where the infrared starts. Is about 0.7 microns. And the question is, what happens to the radiation that's blocked by the CO2? And what I'm saying here is postulating, well, somehow it must be going out all these other wavelengths. Okay, so it's said to be returning to the Earth and then going back out the other wavelengths. And that is, so like I said, there's a postulated curve. So it must be going out other wavelengths. And that's, again, a postulation. So this is an interesting area here, too. This is, again, on the higher, a longer wavelength IR radiation. This area is nearly equal to that of the left. So we're seeing an increase in radiation out here. And generally, in the discussions, we're not going out into the far infrared too much. But you see a huge amount of energy that's leaving the Earth in the far infrared. Okay. So the suggestion here is that maybe this bite is coming out over here. Okay, so that's the point. Is first of all, the energy has to be going somewhere else. Okay, so this radiated energy is being blocked by CO2, presumably is coming back to the surface of the Earth, also is being transferred to molecules via collisions, which is called conduction. So this energy then is going to other molecules or back to the surface and then is being re-radiated. Importantly, the radiation is at the speed of light. So this all happened very fast or very quickly. So the question is, if the Earth is even just staying the same because of the increase in CO2 concentration, then this area under this curve has to be the same. Okay, so that's not what we see unless the curve has been altered to have the equal area for a higher wavelength on other frequencies. Does that make sense? Okay. All right. So basically, that's what this says. And again, this is a postulated line that's sort of meant to be it's of an average. It's of the if you were to smooth these out. So often we see that this line is drawn for a black body temperature for comparison, as it says, but that is not a reasonable temperature comparison because it needs to have the same area as the area under the curve. And if you were to take that area and calculate the black body temperature at which that area would be subsumed under, then you would have a different temperature for the planet. So some of so again, what we're doing is looking at the problem from a different perspective, recognizing that the graphs that we come to know as supporting the greenhouse gas theory are not actually supporting it at all. They're undermining its credibility because they're showing that we're missing some energy, and we've got to know exactly where it is. Okay, and so again, it doesn't matter how good your theory is or how smart you are. It matters only if the evidence is in support of your theory, and if it isn't, then your theory is wrong. And so this is a direct theoretical challenge, basically. Okay, so importantly, if indeed energy is leaving via these other wavelengths from the planet, then Schwarzschild's equation, which is used by the IPC and other authors, it cannot be valid. And this basically, as it says, it contains the fundamental physics needed to understand and quantify how increasing greenhouse gases in the atmosphere reduce the flux of radiation to space. So if no other fluxes change, conservation of energy demands the Earth warm. But that's the question. So if fundamentally Schwarzschild's equation doesn't apply, because the other fluxes do change, and they in fact must change if the area under the curve is even to remain the same as if the CO2 bite is taken out. Okay, so this again, then it follows rationally that there's no sound theoreticals because the Schwarzschild equation is fundamental to the temperature variation because it basically calculates the temperature change caused by any changes in concentration for any of the molecules. So if that doesn't apply anymore, then we can't make a connection between the Earth's temperature and the molecular concentrations. Okay, and again, so this means and because radiation travels at the speed of light, any changes in the radiation spectrum can all be very fast and can be viewed more as phase shifts in this radiative spectrum rather than fundamental changes in the temperature of the planet. Okay, so now we've looked at it from a different perspective, and now we're going to get down to the meat of the problem, which is thermodynamics issues. Now, mostly academics and scientists are not experts in thermodynamics, but this is a critical field necessary for understanding any changes in thermal energy or understanding the problems of temperatures. And so if you're not capable in this space, then you really might be not qualified or understanding the real issues. So broadly, the sun provides substantially all the energy to the planet. Okay, so geothermal energy is considered negligible. Now there are some we're looking at amounts of energy rather than where it's located or what it's doing, because there's some qualifications, some caveats on the role of geothermal energy in Earth's temperatures and climate. But fundamentally, from a whole perspective, at least from the perspective of the greenhouse gas theory, we consider geothermal energy as negligible. Because the sun does provide all the energy, and because of Newton's law, a warmer object radiates more energy, then any extra energy must come from the sun. Okay, so if Earth were to have become warmer, then it's going to radiate more energy. Okay, so where does it get the energy from? If the sole source of the energy is from the sun, and the sun we can consider sort of fixed for this discussion, then the sun is going to say, well, I'm sorry, I've allocated the energy that I'm giving you. You want to radiate more, you don't get any more. So what happens to the Earth? The Earth says, I want to radiate more, and it starts to cool. And then as soon as it starts to cool, the sun says, well, here's you've got some more energy. So this is how it maintains thermodynamic equilibrium. So the sun fundamentally is dictating the Earth's temperature, and it's doing so because of something called thermodynamic equilibrium. And what it means is that the only way that we can change the planet's temperature as humans is to change the emissivity, because we obviously can't change the amount of sunlight that we're receiving. Okay, and so that thermodynamic argument is important, and it would have avoided had thermodynamics been more rigorously defined. It would have or utilized, then it would have applied. Is what I want to say. Then we might not have had this massive detour of capital, which is threatening our species and our survival as a species. Anyway, so this says the moon is made of green cheese. Well, obviously not made of green cheese, but if you're told this over and over and over for years and years as you grow up, then if you're asked, well, what is the moon made of, and everybody around you they're all going to say the same thing: the moon is made of green cheese. And well, it's so there are basically two ideas you can be taught, and one is promoted. One are the ideas that are invalid, they're simply not so, and other are ideas that are valid knowledge over some spatial and temporal scope. And so the question is, okay, how do you tell the difference? Okay, so now we're going to sort of step back and say, what I'm going to do is sort of explain why I was able to look at this greenhouse gas theory in a different perspective and understand why it cannot actually be a valid theory. And so this is a question of epistemology, which is the theory of knowledge. Okay, it's a classical challenge. So the classical challenge of epistemology is, how do you tell the difference between knowledge and opinion? Okay, and so the ancient Greek philosopher were first to ask this question, and we call it today sometimes scientific method, but I call it the theory of validation because I've done much work in this area over more than 10 years. So basically, all concepts of knowledge are valid knowledge over some spatial and temporal scope. This is a new law and a principle of an emerging epistemological science, and we can discuss this at another time. But my solution to this classical challenge was to make explicit all nuances of knowledge, whether syntactic or semantic, in a new symbolic representation called the general form. And then I later used this software, an AI software, sold to many global 100 clients and subject to and a company subject to an acquisition offer by a G100 company. And so this is a confirmation of a new theory of validation. So let me I should have put this slide before, but just so you have my background, I was at Cornell in graduate school, and my thesis was AI applications and engineering design. And I concluded that without a science of epistemology, just as we have to have a science of physics in order to have physical sciences, without a science of epistemology, we would never have successful AI. Well, in one sense, I was incorrect because neural networks give us, which are great for pattern matching, have given us a lot of opportunities because computers do that so well. But in another sense, I was right on the linguistic or the language part of it and the reasoning part. And so nonetheless, so what I did is I left Cornell grad school, and I worked for more than 10 years. I was self-employed. I discovered an underlying order in the nature of conceptual understanding that could serve as a foundation for this general form. And that became, and again, it was driven by my desire to solve the classical challenge problem of epistemology. So the idea was generate a symbolic representation that made explicit all the nuances of understanding in the syntax and semantics. That required the derivation of a new lexicological theory, which is a theory of meanings, as well as a symbolic representation. Then a new theory of deduction to show what reasoning was. Okay, so how do we reason from these ideas? And then fundamentally, all this work was a theory of validation. Okay, so then I went to Oxford and I did a full historic and philosophic comparison. This is in the 1990s of my work with the history of Western philosophy. Showed it was solving many of the classical problems of the field, that it was indeed historically distinct. Then because I had undergrad degrees in computer science and engineering, I didn't have an undergrad degree in philosophy. I applied to the LSE graduate program, and I submitted my paper on this validation topic, and they reviewed it, and then they let me in there, and I studied there for a while. I then wrote a book and then demonstrated the theory of deduction, the lexicological theory in the general form, in software that could reason from natural language. So this is a scientific development, an advance in epistemology, which is previously not been considered to be a science at all, but just a branch of philosophy that was under constant speculation. And so, but now we see a science emerging out of this that can be applied for in many things. In fact, we'll see it's the basis for artificial intelligence, educational theory, as well as the other theories, the humanities, all turn to the conceptual model of the human conceptual nature and conceptual knowledge. Anyway, so I doing all this software work, that was great, but I wanted to demonstrate my theory of validation. And I saw back more than 10 years ago, the Vostok cores evidence, the data itself was presented on BBC one day. And I just going through the data and saw that the temperatures were rising generally before the rises in CO2, not the other way around, which meant the causal relationship was inverted. And so that's when I said, well, let me just use my theory of validation and show that it's an improvement in our scientific method and accessibility of the greenhouse gas theory. Okay, so and then from that work, I showed it was indeed invalid theoretically, and I founded the Climate Science Journal. And today, the Climate Science Journal is a little bit informal. It's a journal in the strict sense because I post global temperatures every day. So it's deriving from the French jour. And so it is indeed a journal. It's just in the development stage. Okay. So this is just some backdrop. An epistemological science necessarily had to arrive from outside the academic world. And I know this firsthand. You cannot change something from within. If you have to adopt the prevailing paradigm, learn and study what something that is the prior paradigm, in order to come to the forefront of the field, and the field itself is acknowledged as a non-science, then you're basically precluding any discovery of another paradigm, because you're getting indoctrinated with the old one. Okay, so anyhow, that's the point on that. Now let's go back to the climate science issue. So part of the greenhouse gas theory is the effective temperature argument. It says basically that the temperature of the Earth is much warmer than it's supposed to be. If you were to look at, in calculating the solar radiation meeting the Earth, et cetera. But there's a problem with this idea and this effective temperature paradigm. It basically says that the surface of the Earth is where we stand up. Okay. Well, thermodynamically, that's not true. The surface of the Earth is the edge of the molecules of the planet. That's the surface. Okay, because the surface of the sun is not where we could stand up, right? If we could, but that it's not equal to the density of the surface of the Earth is not where the density is such that a person would float fundamentally. Okay, so the surface of the sun is the extremity of the molecules of the sun. Okay, now you could get more elaborate and say, well, the surface can be when there's only so many molecules. So you have a little bit of a problem. I mean, if you want to know what the temperature of the surface of a body in space is, you can basically, it's the temperature of space on one side of the surface, and on the other side, it's the edge of the gradient of the body. So I say that we should be choosing the temperature the surface of the Earth based upon its thermodynamic temperature. So this is a graph derived again from Noah, actually. And so I took their graph and then made a bunch of notes on it, basically. And so this orange line is their temperature line. Okay, so right here is this high temperature, and that's the one they're talking about as the surface of the Earth. Well, that sounds all nice at sea level, but it doesn't actually. It's not the right place. It's biased by the same problem that Galileo had, which is the anthropomorphic assumption. It's basing our physical sciences arguments on humans, or where we're at. Okay. So anyhow, so this temperature then declines to the tropopause, and then it rises again to the stratopause, declines again to the mesopause. Again, so the actual temperature that the Earth should be, as calculated from given the solar radiation that we receive at the distance, should be negative 16 degrees Celsius. Well, the temperature of the Earth is negative 16. Of the surface is negative 16 degrees Celsius, depending upon where you choose that surface to be. Okay, so we cannot choose it to be down here at where we stand. That is purely anthropomorphic. So it's not a good selection. So the question is, so where do you choose it? Do you choose it? Here's the troposphere, where 80% of the atmosphere is. But I say it should be calculated at the highest extremity. This should be chosen at the surface of about 112 kilometers. Should be chosen as the surface of the Earth, simply because that's where the thermodynamically correct temperature is located. So people could say that the surface of the Earth is too hot it must be caused by the greenhouse gas theory, and that's not accurate. You can say the nitrogen and oxygen are making the Earth warmer at this altitude above the planet, this radius of the planet, but that's really, you can go down a little lower, and down 100 meters beneath the surface, it's going to be warmer still, So, so where are you supposed to choose? Why would you choose where we stand? And from a scientific perspective, it's just not the right place. Okay, so that basically eliminates this defense of the greenhouse gas theory. And so it's because it's anthropomorphic and we can't use it. Okay, so this basically, so this is a bit of a abstract discussion, frankly, when you talk about epistemology and theories, but basically a better scientific method is now available. And what I've done is demonstrate its application to a theory that generally is considered valid by all sides of the argument, including the skeptics, as you are aware. So challenging the basis of this theory is what I've done, and I've used a better technology of validation or an improved scientific method. Okay, and these are the support for an emerging science of epistemology, which is interesting. Again, it's not climate science, but it's interesting because it has implications for all the humanities and for physical sciences as well. Okay, so I don't want to spend a lot of time on this. Happer and this gentleman's, I don't even want to try to pronounce his name. They have a paper, and I got some gripes with it because of what they call climate forcing. And so I wanted to challenge it. And basically I exposed the argument of the paper and evaluated their premises and confirmed that their conclusions are invalid. Okay. And basically I see, so force equals mass times acceleration. There are half a dozen force formulas that are derived through the history of science, and they all are at the basis of science. So when we start throwing in a cavalier way the concept of force around and attach climate to it, we're basically we're destroying the foundation of science, of scientific enterprise. And you'll see that there is no justification for this so-called infrared forcing or climate forcing that they're discussing, and they're obliterating the language of science by their perspective and ineptitude. And so that's why I'm taking issue with this particular paper. Okay, so their paper is basically talking about the molecular concentrations of the atmosphere, and it attempts to correlate temperatures to those various molecular concentrations reasonably enough. Doesn't really make any difference. It doesn't have any, fundamentally though, it doesn't say anything about the temperature of the planet or any forcing of the planet. It's saying that the concentration of these various things will affect the temperature at a particular location, but not of the planet, just of a particular location. We already know that the planet's temperature cannot be altered because the sun is dictating that temperature. Okay, so there's only one way that we can alter the temperature of the planet, which is changing in emissivity. Now I'm just going to digress real fast here. We do actually change emissivity on the planet Earth. We can change it by roads, by rooftops, any alteration of the absorption of the surface will change the emissivity. Even a solar panel will warm the planet because it absorbs more energy than Earth in general. If you put it over a field of snow, for example, it's going to increase Earth's emissivity. Okay, so that means that it will, in fact, from a thermodynamic foundation, it will change Earth's temperature, and it is a human change. But we're not talking about CO2. The CO2 is the issue of the greenhouse gas theory, and that is invalid. Humans changing the Earth's temperature? Yes, possible. We can, run nuclear power plants all day long, all over the place, and that will warm the Earth and so there are ways humans can change the temperature of the planet, but CO2 is not one. Okay, and this basically is this. People can look at this later, but it's basically saying that thermodynamics, being sort of a statistical business, has to be when we're evaluating a theory, we have to think a little bit harder. We can't just you just can't go into and make all kind of assumptions like, okay, so it's blocking some radiation, therefore Earth gets warmer. That doesn't actually follow, okay? Because there's other issues that precede it, and thermodynamics is one of them. And this is so I use the analogy with Happer's paper. They could be saying that salinity levels in the ocean, if you altered them, this is the same sort of argument. If you change the salinity levels in the ocean, can we say that if the Earth had a more salty or actually the specific heat capacity is less, but if we change the salinity of the oceans, wouldn't it absorb more energy at various levels or less energy, depending on how the change was? So I say this is an analogy which shows that their attempt to equate concentration changes in the atmosphere to global changes in Earth's temperature is bogus. They don't have any, this argument has just as much merit, okay? But again, it doesn't hold. And this is sort of an example pulling it out. This says here the salinity of 0 grams per kilogram and then rising. And it shows that the specific heat of salt water declines with an increasing concentration. Okay, so not that everybody wants to remember this because it's sort of esoteric, but nonetheless, and we look over here at CO2. CO2 has a lower specific heat than air, nitrogen, or oxygen. It means it takes less thermal energy to warm CO2 than air, and therefore CO2 holds less thermal energy at a given temperature. It means that CO2 can, when we have higher concentration of CO2 in the atmosphere, it can warm less ice, not more, because it has less thermal energy with which to transfer. And it's the same. If the salinity of the ocean increases, then it can store less thermal energy on a per unit basis. And so this is, it's counterintuitive. But so anyway, so when I originally wrote this slide, I said, well, I think salinity will increase the specific heat capacity, but it actually doesn't. It works the opposite way. And the same that we're, so we can, so like I said, you have to consider all these things in order to be able to have valid conclusions. Okay. And it does raise this question: what is the role of specific heat capacity in affecting Earth's emissivity? Emissivity being a fundamental thermodynamic property of the planet that we have very little understanding of on a global scale. Okay. This is, I just pulled this from their paper again. And basically they use the temperature here of black body temperature. And then they're basically saying the red here is where they have an increase in CO2 concentration. And they're saying that this is look, it's absorbing just a little bit more thermal energy, right? Or infrared radiation, however you want to say it. And therefore, what I say is, wait a minute, you're saying that it's sending less to space. You're saying that a little bit more concentration of CO2 is going to make Earth look cooler from space, not warmer. So this is a contrary. So they're not seeing the evidence that they're presenting and its implications from different perspectives, which is what we're supposed to do. Is we have to look at the world from a rational perspective. Anyway, so this is, basically here's the green, which says no CO2. And if this were the green, then the area under the curve would mean the Earth is warmer without CO2, okay? And not cooler, okay? And there's other ways we could look at this. We could take this onto a different direction. We can say, wait a minute, if the Earth is cooler from space, then is that bite due to the plants absorbing CO2? Because that has to have an influence, because plants photosynthesis is an endothermic reaction, so they're absorbing heat. So is that why we have the bite? Are we misconstruing its origins? We know on the one hand that it is absorbing the radiation differently than the other molecules. So that's the one. But is there a coincidental role of photosynthesis and reducing the amount of energy that's leaving the planet? These are good questions, right? And need to be further examined, because photosynthesis also absorbs thermal energy from the air, not just photons directly from the sun in the process of heating and warming up anyways to cause the reaction. Okay, so that's like I say, those are just questions. And this is another quote. He says, thermodynamics is the only physical theory of universal content which I am convinced will never be overthrown within the framework of applicability of its basic concepts. Again, this is a bit of an appeal to authority, so that's a fallacy. But fundamentally, I use it to endorse the idea that thermodynamics is very sound because it is statistical physics. It's a very powerful body of knowledge, even though it's not universally understood or as well as it should be. Okay, so in conclusion, modern academics have a lower epistemological standard, and this is a bold statement I'm making, and from my perspective. Okay, so you don't have to agree with everything I say. What I'm doing is looking at the world and our cultures and the state of our knowledge from another perspective. So just because it's another perspective doesn't mean it's wrong. It could be better or it could be worse. And so, but it is different. Okay, so because it's different, you might consider it. But when I start to show you that maybe it's a little bit more profoundly better view of the nature of conceptual knowledge, then you can start to gain advantages from it. And one of those is an improved theory of validation or a better scientific method. Okay, so what I'm saying here is modern academics have a lower epistemological standard than productive society if they are not verifying their data and conclusions with either experiment or productive application. And I know this. I've worked in both sides. I'm in science as well as application, in manufacturing as well as computing. And I know that if you have an idea, you need to test it in the world. And if you got to deliver it to 100,000 people, you got to do a lot of testing, and you discover a lot of things. I've discovered lots of things about my theory of deduction by building natural language reasoning systems and improve the theoretical foundations. And so that's how that works. And when today we've got basically a nationalized academic world globally, and this is a threat to our cultures, because this nationalized group of people are at great cost. They're undermining our standards of knowledge when they're supposed to be doing the opposite to maintain them through education. They're undermining our general standards. Okay, so greenhouse gas theory is on par with alchemy or bleeding patients to heal them, both of which were considered science in previous societies. Yeah, but yet the greenhouse gas theory is not science now, nor has it ever been scientifically grounded. And finally, this is a little bit, since I'm using a new theory of validation, it applies both to the concepts of the humanities as well as the physical sciences. And I think that the greenhouse gas theory is being used for political purposes. And I think, therefore, it's important that we challenge a theory for other reasons, because it will undermine the credibility of any of its use to challenge the fundamental theory. Okay, so let me see if there's anything else. Okay, yeah. Well, today there's a total solar eclipse on a broad swath of the United States. So people should get out there and take a look. I'm not going to be able to see that from where I'm at, but basically the temperature of the air at the Earth's surface drops 5 to 20 degrees in 20 to 30 minutes, or about an hour or whatever. And what does that mean? Okay, so if the sun is blocked, and within an hour the temperature drops drastically, where the heck is the greenhouse? Okay, it's not there. It's not functioning. There is no greenhouse. There is the CO2. I mean, nitrogen and oxygen are holding thermal energy, but there is no greenhouse. And without the sun, we would freeze in a very short time. But I just want to reemphasize this, that the greenhouse gas theory is not valid scientifically. If anybody is out there in a total or generally partial eclipse, then they should go out and see how cold it is. I was in one once in Georgia, and it was amazed how cold it got, how the traffic lights, the road lights turned on, and how you needed a sweater, and because the sun was immediately taken away. But anyhow, okay, and let me see, and that's about it. If you want to contact me if you were interested in any of my books, and I can discuss or give you links to that. And you got any questions for me, Tom?
I do. I don't know if you want to comment on other people's work, but on my podcast, we've had Young Tuition, Marcus Ott, Tom Shula talking about some of this stuff. And do you have any comments on whether they are on the right track, or have you looked into their work?
Yeah, I have talked to them. I've been in communication with them. I don't want to. I can't, like I said, I'm not a master of their particular work, but I have, like I said, there was I have been in communication. There's a lot of really good work out there, and people are when I challenge, other people challenge, and then I've found some other, so I'm not the only person challenging theory. You kind of see the world from your perspective. They don't have much choice, Then you listen to other people, and then you try to update your perspective so that it's accurate. Okay, this is the challenge of a mature human being, is to try to see the world for what it is. And so am I the only person that's challenged the greenhouse gas theory? No. I mean, we can go back to Avogadro challenged Arrhenius's perspective back, in the early part of the 20th century. So no, I'm not the first person, but I'm one of the first anyways to take a direct attack at the theory itself. And the ways that I've challenged it here are novel. So they are original. I did look how can the Earth, because the Earth is cooler from space. If you look at it from the perspective of space, this is a relativistic issue. And then the question of effective temperature, that's not, from my perspective, been challenged in that manner before. Again, you never know if you're the first guy on Earth to invent the light bulb, or where there's some guy, 200 miles away, he's doing the same work. You do the best you can to innovate, and then check your work, and then this is a scientific enterprise is a labor of love for those who participate, and it's not necessarily remunerative. It doesn't necessarily pay much, but you do it because it's sort of an evolutionary drive, I suppose. I think that basically what we'll find is that people, if it's clear to people, they have to double check it and think for themselves, but they should spend a little time thinking what I said in the beginning and understanding what that fundamental challenge is. And then they start to have to, they've got to man up, or, they got to have some courage and start to challenge the arguments, the scientific basis of the theories. And when they do that, the Marxists will quickly capitulate. And the people promoting it when they know it's not necessarily legit, and not everybody is dishonest. Some people are just duped, and then some people know something's up, but there's money in it, so they don't really care. They don't want to ask too many questions. So you have and then some people are just pushed along by peer pressure and don't want to go against the crowd. But sometimes things get out of hand if we don't stand up and assert a better foundation for general knowledge or scientific knowledge. And there's a time when we have to do that.
Actually, this might be a dumb question, though, but that bite that you talk about, that part of it is real, you think, right? That CO2, could we still call CO2 a greenhouse gas, but other parts of the theory are not right? Or no?
I wouldn't go there. I would say that it's definitely absorbing energy, but it's from my perspective. Okay, and this I still have to do a lot of work on verifying, but I would say that it's only a phase change, and it is not a greenhouse gas in the least. It doesn't warm the planet, and it doesn't. It's I had a picture before on the last time I did a presentation with you. Of a molecule of CO2, and it showed it where it absorbed a photon and then it radiated a photon, but basically when a CO2 molecule absorbs energy, it's got it. Then it radiates it, and then it's gone. And so the photon was going past anyways, and now you're talking about a sub-second, tiny nanosecond of time, or microsecond or whatever, when it's actually it has this energy, and then it's going to pass it on as if it never had it. So what difference does it make? My perspective is just it's a ludicrous theory, and like I said, this George Washington, the first president of the United States, is a brilliant guy, wonderful general, fine character. He basically he was bled to death. He got sick, he got a flu, he was out in the cold, and they bled him and then bled him and bled him some more. And he died, and largely from being bled, because that was the technology, the latest, greatest technology of his time, and that's what happened. And so we don't want to bleed humanity to death with by eliminating our sources of energy, which is what I see we're doing.
So just to be clear, though, you do think that when CO2 absorbs that photon, it is different than what nitrogen does when that same photon comes at that part is correct.
Yeah, it is. It does. It does have the vibration rotation does of the molecule does allow greater degrees of freedom for a CO2 molecule and multi-atomic molecules than nitrogen and oxygen, which are diatomics. Okay, so they can't have as many degrees of freedom. On the other hand, as I said on our previous podcast, nitrogen and oxygen also absorb energy by electronic level changes. Okay, so and this is also augmented by Rydberg-Ritz theorem, and basically what it means is that there's a whole bunch of frequencies in the longer wavelengths where nitrogen and oxygen are absorbing radiation. That's in the combination principle, where it's basically so we don't. They're fuzzy lines, so to speak, and because of the nature of this of the quantum levels of molecules. So that's sort of my perspective is, yes, CO2 definitely has a there's a word I haven't been able to find, but there's it's selectively, that's the word. The CO2 does selectively absorb IR radiation in that spectrum, and that can be attributed to CO2. And like I said, with a caveat that it also might be indicative of something being absorbed on the ground through photosynthesis, perhaps of phytoplankton or plants or something. I don't know. And more work needs to be done. It's controversial stuff when you get into this because people want to defend their view, and that's a competition of life, and so it's not. I'm not afraid of it. I stand up to it, but we all need to fight to understand what's the accurate knowledge and what isn't.
So we're not naming any names here, but do you get the sense that there are some famous folks in this debate who think you may be on the right track, but they won't say that publicly yet?
Well, yeah, yes. I won't name any names either. But no, I would say that there are people who have endorsed the greenhouse gas theory for decades. Okay, so for them to have to eat their words, is not necessarily a exciting part of their life, right? so they're so a lot of people and people need others to confirm to them that something's right. Peer review, okay, I would look for an example. Peer review is where you go and you need somebody else to tell everyone else that you're right, okay, or similarly. It means that you're allowed to say what you have to say in a formal society, and if you don't have the endorsement of some group of people that have control over the peer review process, then you're not allowed to say these things in society. And it may not be simply because they're wrong. It may be that the vested interest of the people controlling the peer review. Or like I never submitted my work to peer review. What I did is I went to PhDs in atmospheric physics and physics and I got them to read it, and then they sent me endorsements. So I did it, This is a little different. I knew in advance, I knew the controversial nature, and I understood I saw guys like, gosh, there's so many people. I've seen the people just rage through that were terribly chastised because of their views in science and wrongly. And I saw that already. I said, okay, well, these guys are not your allies. And when I understood there was a Marxist rule, they want to basically say capitalism caused CO2 rises, and CO2 rises is evil, therefore capitalism is evil. That's a simplistic argument, but it's the one that they don't want to say because it's so simple, stupid. But it's the one behind all their machinations. And so when I understood that, I knew, well, these people are there can be some pretty horrible people. They're trying to basically steal everybody's property and enslave them. That's the Marxist pseudo theory. It's pseudoscience. It's rubbish. And I can go through a book on Marx and show all the premises invalid, and they generally reason appropriately from invalid premises to reach invalid conclusions, but that doesn't make it anything other than pseudoscience. Nonetheless, so I would say it's impactful, but it takes time to influence a scientific community when your views are distinct and they differ and challenge the prevailing paradigm. I knew it already. I call it the innovator's dilemma, even though that's applied to something else. As an innovator, if you're too innovative, you just got to bear with it. That's what you did. That's who you are. You sing your song and hope that one day people will stop, but there are a lot of nice people out there. And I do get a lot of confirmation. I have 35,000 people in my network, that are reading, my posts all the time. And I have, Twitter network or X network or whatever. And so that's growing. And so I do, and it does. I do think it impacts the conversation. And I know this. I'll give you an example if I might. I was invited by the Nobel Foundation to a conference in Washington D.C. last May on knowledge or something, and so I went up there and I prepared a little paper, and it was hosted by the National Academy of Sciences. So I went up there, and I've got a long history in business and all. So I went and basically introduced myself to about 50 or different people, and gave them my paper and made my little pitch. I pitched to Nobel laureates in physics, the president of the National Academy of Sciences, the head of sciences in the UK, so all kind of people, and it was interesting. But like I said, there's some better things that I'm working on that could have a more profound influence. So we'll see. But like I say, my drive was to I kept true to the temple of epistemology and science, and I had to digress for, like I said, more than a decade, and in order to devise these things. And I just to give you a little bit of insight, I brought 10 books. I had a farm. I said, well, farm, because it's not this competitive, and you just have to wait on plants to grow and sell them. And so I did, and I did this on the edge of a jungle in Central America, frankly. And then I built up a little farm and served all the hotels and supermarkets and restaurants. But at night you can't do anything on a farm because you got no energy. And I would just work on epistemology. But these 10 books, they were broad subjects, different subjects. All about a few hundred pages long. I had a nice sample size of these 10 books, enough, because it wasn't all modified or contorted to somebody's epistemological bias. They were just expressions of views in different fields. So that was from that sample size is when I basically discovered the underlying order, the nature of conceptual knowledge, and that then became the foundation for generating the general form of a concept, which then became the basis for our data structure in software. And then, of course, we have a lexicological theory, which is a real big part, so that computers can understand the meanings of words. And then the theory of deduction provides us a capacity to reason from languages, or from natural language with computers. So it's cool stuff, and it's applicable, which is an endorsement of the work as an emerging science of epistemology. So anyways, like I said, I'm going a little digression there, but anyhow.
Okay, thank you very much. A very interesting presentation. And as usual, I'm going to put the PDF up on my Substack so people can take a look at the slides from today. But thanks again for doing this. I think a lot of people are going to be commenting about it. So I'm looking forward to that. Talk to you soon.
Thank you, Tom.
Bye.
Yeah.